Hello everybody, my name is Mr. McAllen, and today I want to talk to you about how to find a derivative of an inverse function. In order to do so, I have to take you through a few quick points. We want to first talk about a function at some points compared to its inverse. We want to talk about a function and its derivative at some points, and we want to compare it to what is a known inverse function at its points. And then we want to do a quick example for an AP test, just to show you how these concepts apply. Most fundamental concept with an inverse and its function is the switching of the xy pairs. So what we're going to do in the first part of this example is we're just going to draw out what x squared is at certain points. Now if I plot it at 0, 0, 1, 0, 1, 1, then I go to 2, 4, and then 3, 9, I would have my first set of points. And if I plot the points on the left, I would have symmetry for the parabola, but my function would not be 1 to 1. So I'm only going to plot it in a restricted domain where I have the function plot at these points for when x is greater than 0. I'm going to label the points so that we can recognize how the points are being flipped when we talk about our inverse function. When we draw our inverse function, and I'll just refer to this as going over to here as inverse land, x's and y pairs switch. So 0, 0 switches to 0, 0. 1, 1 switches to 1, 1. 2, 4 switches to 4, 2. And 3, 9 will switch to 9, 3. So I'm going to have to extend that out, and we're going to be at, this will be 5, 6, 7, 8, 9. That's approximately correct there. So we'll see that, and we should all recognize that this function, the inverse function with a restricted domain of x squared, is the square root of x. This is going to help demonstrate my point for the derivative of its inverse, because the next point is let's analyze the derivative at some points for both functions. For example, if we do the derivative at 2, 4, so we would take the derivative if y equals x squared. We would take the derivative using the shortcut. It would be 2x. And now, if we evaluate that derivative at x equals 2, we would get a slope of 4. So I'm going to just draw a slope of 4 in with a red tangent line. And we can see that that would be an approximate picture of a line with a slope of 4. Now remember, the important thing to remember about inverses and functions is that between the function and its inverse is the x and y switch. So, would it be any mystery that the change in y over the change in x should also switch? So essentially you can think of it as being the change in x over the change in y. So if we go to the corresponding point, 2, 4, over on this side, that would be the point, oh, excuse me, that's not the wrong point, 2, 4 is right here. What would the slope be? Well, if x's and y switch, and change in x over change in y switch, then would it be any mystery that the slope here would just be the reciprocal of 4, and that would be 1/4. Well, let's check this hypothesis. What we'll do is we'll take the derivative of the known inverse function, so y equals x to the 1/2 power. Then the derivative would be, bring the half down in front, x to the negative 1/2. That would be just 1 over 2 root x. And remember, these x values here refer to the x values for the inverse. So this would be 1 over 2, the root, since this point here is 4, 2, I'm going to plug in a 4, and lo and behold, my slope value is 1/4, exactly what we expected. We can try that again for another point. If we try the slope at 3, 9, what you'll find is that you'll get a slope using our equation of 6. If you come over to this point at 9, 3, and you plug in the x value into this equation, you would have a slope of 1 over 2 root 9, which would give you a slope of 1/6, showing that not only the xy pairs switch between inverses, but the derivatives become the reciprocals at corresponding points. So let me write that down. The derivative of an inverse is the reciprocal of the function's derivative at corresponding points, or at the corresponding point. That's a very important point. So, when we look at an AP problem, they would say to us, as an example, they would show us, we'll just use this quick example, they would state the following. They would say that f of x is equal to x cubed plus 2x. They would not give us a graph. And they would say that the function, because of an inverse property, f of g of x equals x, this is a property of inverses. So they would give us the property here stating that we have the inverse function. They would then have us give us a point on the inverse graph. So they tell us that g of 3 equals 1. And that is the connect, and ask us what the derivative is at g prime of 3. So let's just draw a little map to show what's going on. Here's f of x, here's the inverse. We don't have any points for f of x, but we do have a point for g of x. We know that g of 3 equals 1. So that maps back to the inverse and tells us that we know a point at 1, 3. If we know a point at 1, 3, we can, and we have the equation for the function, we can find the derivative at 1. Well, the derivative function would be, using the power rule, 3x squared plus 2. I would plug in the 1 value, and that would give me a value of 5. And now I know what, when I go back to this point, since the slope here would be 5, I'll just draw something that resembles a slope of 5. So that if that line had a slope of 5, then when I came over to this point, I would have a slope of, you guessed it, the derivative at 3 would have a slope of 1/5, because of the rule that the derivative at corresponding points is a reciprocal of the derivative of the function at the original point. So let's review this one more time. They tell us that f and g are inverses. They give us a point of the inverse function at 16, 4. We know that this is a parabola, but we're going to pretend we don't know the function. And we know that if we can find the corresponding point, will be at 4, 16. Now we know the corresponding point, so we can figure out the derivative of the function. We can evaluate it at the point. And because we have that information, we can now, I'll just draw in here a slope of 8. We know that when we map to the corresponding point in inverse land, the slope here would be the reciprocal, and this would be 1/8. Now drawing in the original function, you'll see that we have the parabola here, and then here we'd have the square root function. So you would see that, in fact, you could see the properties of the inverse function where x's and y switch. and the derivative dy dx for the function switches to the value of what dx dy would be for the corresponding point in the inverse.